Good morning, students. Our today's topic in the subject of physics O levels is sound. So concentrate yourself. We are going to start now. Sound is caused by vibrations and is a form of kinetic energy. So the first point to remember is sound is caused by vibration. So anything which vibrate produce a sound. For example, when you place your fingers against your throat, you will feel the vibrations of your vocal cord when you talk. Like when you feel this one, here is the vocal cord, you will feel the vibration. And this vibration actually produces the sound. When a tuning fork, a small U-shaped steel instrument is struck, the prongs vibrate. These are the prongs. And we hear a musical note. So actually these are the prongs and this is a tuning fork. And when we struck it with our finger, the prongs vibrate and we hear a musical note. If the vibrating prongs are quickly dipped into the water, we see that the water splashes because the prongs are vibrating. That's why a splash is produced in the water. The audible sound is 20 Hz to 20,000 Hz. This is known as the range of audibility for humans. Sound frequencies above 20,000 Hz are known as ultrasound, and below 20 Hz are known as infrasound. So these are very important points. So the audible range for the humans is 20 to 20,000 Hz. The sounds having frequencies above 20,000 Hz are known as ultrasound and below 20 Hz are known as infrasound. So here is a video that will make your concepts more clear. So look at the frequency is increasing. The range for the audible sound for humans is 20 to 20,000 Hz. Mind it, here is the frequency increasing. Still we can hear the sound. But when the sound will be greater than 20,000 Hz, we will be unable to hear the sound. Look at the frequency and look at the wavelength. Now you can hear the sound. Can you hear the sound? And one stage will come when we will be unable to hear the sound. So 20 Hz is the minimum level of the frequency that we can hear, and 20,000 Hz is the maximum that we can hear. So look at the frequency and look at the wavelength now. Okay, moving further. Next topic in the lecture is how do the vibrations travel to our ear. So look now, if you look closely at the spring, you can see that at any instant, some parts of the spring are pushed closer together. That is called compressions or squashes. And some parts are pulled further apart. And that portion is called decompression or rarefaction or stretches. The type of the waves are called longitudinal waves. So this is a spring. You can see here the spring is compressed and here is pulled further apart. So this portion is called compression and this portion is called rarefaction. It is the same with the sound wave in the air. In some places, the molecules of the air are pushed together at slightly higher pressure, that is called compression. And in some places, the molecules are further apart at a slightly lower pressure, that is called decompression or rarefaction. So, likewise of the spring, so same kind of the waves travel through the air of the sounds. So at some places the molecules are compressed and at some places the molecules are rarefaction in the form of the rarefaction. So this is the graphical representation of the sound. At some places the molecules are in the form of the compression and at some places the molecules are in the form of the rarefaction. So molecules pushed further molecules, and like in this form we can hear the sound from which was produced from here and reach to the ear of the person. These compressions and rarefactions shoot across the room to your ear, traveling at the speed of the sound. Molecules of air do not travel across the room. So this is very important point to remember. Molecules of the air do not travel across the room. They just vibrate to and fro and pass the energy to the next molecule. The wavelength lambda of the sound is the distance between two successive compressions or rarefactions. So here are two successive compressions or two rarefactions. So the distance between the two successive compressions or rarefaction is called wavelength of the sound. The formula for the speed of the sound is frequency multiplied by wavelength. Frequency is represented by small v, frequency by small f, and wavelength by lambda. So v is equal to f lambda is the formula for finding the speed of the sound, where v is the speed of the sound, f is the frequency, and lambda is the wavelength. Sound needs a medium, that is gas, liquid, or solid, for transmission. So this is very important point to be noted. Sound cannot pass through the vacuum. Sound needs a medium for the transmission, and medium may be gas, liquid, or solid. Unlike electromagnetic waves, sound cannot travel through the vacuum because there are no molecules to pass on the vibrations. Air is the main medium for us to hear sound. You can hear someone through an open window even if you cannot see them. That is because sound waves spread through gaps or bends round obstacles of a similar size of their wavelength. The effect is called diffraction. So it is very common experience that we can hear these sounds from the other room or from outside of the house because of the bending effect of the sound. This is called diffraction. So point to be noted. Sound travels faster in denser medium. So this is another very important point to be noted. Sound travels faster in denser medium. So it travels faster in liquids than in gases and fastest in solids. So more denser the medium is, the sound will travel more faster through the medium. Sound travels faster in higher temperatures. So this is an other effect which affect the speed of the sound. So sound travels faster in higher temperatures. At 0 degrees C, the speed of the sound in the air is 331 meter per second. At room temperature, the speed of the sound in the air is faster, about 340 meter per second. The speed of the sound does not depend on the pressure of the air. Apart from media, speed of the sound also depends on the temperature and humidity. Sound travels faster when humidity rises. So, it means the speed of the sound depends upon three things. Number one, the medium. The denser the medium is, the faster the speed of the sound will be. Number two, the temperature. The higher the temperature, the more will be the speed of the sound. And number three, the humidity. The more the humidity, the more will be the speed of the sound. Here is a video that will make your concepts even more clear.
Transmission of sound. Every sound is produced by a vibration. Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat. You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves. There are mainly two types of waves, transverse wave and longitudinal wave. Let us see how waves travel. We can use a slinky spring to observe both types of waves. Emily is holding one side of the slinky, while Dr. Zook is holding the other end. With a quick upward flick of the wrist, Dr. Zook has sent energy traveling through the slinky. Notice how the slinky moves? This is a transverse wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. The wave traveled from Dr. Zook to Emily and back. Now let's see what a longitudinal wave looks like. Emily is holding one end of the slinky, while Dr. Zook is pulling its other end towards himself, and then pushing it towards Emily. Watch closely, and you will notice that some of the coils crowd close together, and then slowly move farther apart. This is because the vibrations are parallel to the direction of the wave. If the wave moves from right to left, then the particles also vibrate from right to left. This is a longitudinal wave. Sound waves are longitudinal waves. These waves travel at different speeds in different mediums. The medium could be a solid, liquid, or gas. Now let's see how this works. In a solid, the particles are very close together. Sound energy moves.
So this is the reason why sound waves travel faster in solid as compared to liquid and gases. So look at the reason.
As one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them. Now we know how sound travels in different media. The vibration of particles produces waves. Wavelength is the distance between two consecutive compressions or rarefactions.
So this is the wavelength between two successive compressions or rarefactions.
The number of waves passing through a point in a second is called frequency.
So this is the definition of the frequency. The number of the waves passing through a point in 1 second is called the frequency.
And it is measured in hertz.
And the unit for the sound is hertz.
Sound waves travel in all directions. Sound gets reflected. That is, it bounces back on hitting a solid surface. Bouncing back of sound is called echo.
So this is called echo, the bouncing back of the sound from a solid surface, and this thing we will read later in the same lecture.
Bouncing back of sound is purposefully used in detecting depth of seabeds. That's amazing, isn't it?
These are the functions of the echoes.
Every sound is produced by a vibration. Vibrations are produced by our vocal cords when we speak. There are two types of waves, transverse wave and longitudinal wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves. Sound travels quickest through a solid. Wavelength is the distance.
So students, this was the first lecture on the topic of sound. I hope so this will be much interesting and easy for you to understand. So read this lecture again, understand it, learn it, and make your notes. Thank you so much.